All right, Algebra, welcome back. Hopefully it was helpful to get some extra time with your work from last class where we were finding rate of change. And if this is still a little rough from you, please don't panic. We're going to get more practice. We're going to do multiple loops with rate of change, all right? So this is one of these concepts where we're going to kind of loop around, and we'll have a time to practice it a bit, and we're going to loop around again, and we're going to have some more opportunity to practice it, and we're going to loop around again. And rate of change is something we're going to make multiple loops, and you'll get multiple opportunities to kind of get practice with this, and multiple chances to really get this down, all right? Do your best. Spend your time in class. Spend 10-15 minutes max outside of class for each class day, and then come see me when I get back if you're still having any kind of a struggle, but we don't have a quiz on the horizon just yet, not until after I get back, okay? So just do your best in class, get help in class, and then you're doing your best, and that is all I'm asking from you right now, all right? So we're going to look at this new concept here of determining if a function is linear from a table. So let's just review real quick this concept of if a function is linear. We've talked about is a function linear or not linear before, and I have a little thing set up here. You do not have to copy this. I'm just reviewing. So we've talked about is a function linear or non-linear before, and we've looked at this in terms of their equations. So we said a linear function, our variables have to be to the first power, but that we don't care if we have decimals or anything with the numbers, that's okay. What we can't have is variables to some power other than 1. We can't have variables in the denominator. Deny the denominator. We can't have variables in radicals. Those were our problems. Those are nonlinear. And then we've looked at their graphs and said that linear functions are going to have a single straight line graph, whereas nonlinear functions have any of our kind of hinky things. So they might be curvy. So curvy was one, or we had maybe they were made up of multiple straight lines instead of a single straight line. These were non-linear. So now that we have explored this concept of rate of change, we are going to have a chance to get some more practice with rate of change as we look at how to determine if a function is linear from its table. I'm going to ask you guys to just read this key concept to yourselves real quick. And I apologize, this recording system doesn't allow me to pause my recording, and I do need to respond to a text. So read this to each other real quick while I respond to this. Okay, so what we have here is that linear functions have a constant rate of change. And what we want to do for this key concept here is pull this apart. We're going to annotate again. So remember, when we annotate, this is something you hopefully have seen in your English class. There might be an extra T in there, I'm not sure. We add notes. Right, this is an important deep reading skill, which is important in our math class. We're going to add some notes to this key concept. So linear, remember our linear functions form straight lines on a graph. So we want to keep that in mind. These are our straight line functions. A function is just a type of relationship between our x and y values. Remember, x comma y. Okay, it's a type of relationship between our x and y values, and it's a special kind of relationship. If you remember back to our domain and range, where each of our x values has only one y value. The important thing right here is that this means that we can have a y equals number constant, like y equals 5, where we get those horizontal lines. These are okay. What we cannot have, these are okay. What we cannot have in functions is x equals 5 or vertical lines. And we're going to see this a little bit later. These are not okay. Okay, oops, well, x isn't great. We're just going to cross this whole thing, circle it, and cross it out. There are no x equals a number in functions. Okay? And then we're going to skip over here a moment to this rate of change, because this was the new thing here. And this is a good chance for us to review. Our rate of change is our change in one quantity. Specifically, it has to be the change in y. And remember, let's add here, change means subtraction. The change is the subtraction part. The rate is the division part. When we say, what is the rate? That is, means I'm going to deal with some kind of division. So rate of change means the division of my subtraction. And specifically, our rate of change is our change, subtraction of y, over our change, subtraction of x. And this was our new thing we're going to get more practice with today. This is one of our loops. Okay? So I'm going to take a moment. We can all kind of get caught up with that. And then the last main thing that we want to annotate is this word constant. I want you to think, what does constant mean? If something is a constant in our life, or if we say that God is constant, if we hear the phrase, God is constant, and what fills the blank in our mind? God is constant and hopefully, what comes to mind is unchanging. Constant means unchanging or stays the same. Something that is a constant in our life is always there. It's always there for us. And in the context of math, a constant is a value we talked about that does not change, whereas variables change. Variables are things that change. Constants stay the same. Okay? So constant is something that stays the same. So it's kind of this weird idea. A rate of change is something that changes, but we want a constant, we want an unchanging rate of change. What does that mean? That can seem like a contradiction in terms. And sometimes things that seem like a contradiction on the surface aren't really. It just means that they're complicated. So we're going to get into this a little bit, and that's all right. So what does this mean to find a rate of change that is constant? It means that we're changing at the same rate. We have a steady change, all right? So again, I need to respond to a quick text. Take a moment, and I want you to read through this process, and I want you to underline what you think are either 3 important key terms or 3 terms that you say, this is something that I could use some explanation about. So 3 important key terms or 3 things you could use some explanation about. And you don't need to tell anyone whether it's something you think is an important key term or something you could use explanation about, but you're going to underline 3 of those. You can take about 15-20 seconds for that. And then you're going to show your partner the words that you underlined, and your partner's responsibility is to try to give the best explanation of those words that they can. So we are going to try to define these key terms or possibly unfamiliar terms for each other. And if your partner's not sure, then you can go ahead and give it a try and help them out in case they don't know. So go ahead and take a moment to do that. Okay, so as we go through this lesson, we'll go ahead and wrap that up. 3, 2, 1, Red Robin, young. Okay, all right, let's go ahead and practice finding our rate of change. And what's going to make this most helpful is if we really just kind of work from the top down, okay? So remember our rate of change, and I'm just going to write this off to the top, off to the side here. Our rate of change is our change in y over our change in x. And one of the subs asked me, she's just like, oh, sometimes they subtract one way and sometimes they subtract the other way on IXL, but you did it this direction and sometimes IXL did it that direction, and how do you know which way? And when I was introducing the idea to you, I'm always going to use the traditional way just to start, and then once I've practiced with you more, then I'll start to open you up to the fact that you can actually choose as long as you're consistent, okay? What's important is that we always use the same direction, whichever direction we're going, all right? So I'm always going to go bottom minus the top like this, just to be consistent, all right? That also means when we're doing a table with x values, that's going to give us a positive x, because we always line our x values up from least to greatest. So my rate of change, well, let's just start by let's kind of make a little table here, okay? Do a little table here, and we're going to make some little extra tables just to kind of help us out. And this is going to be my change in x table. Now here's kind of the weird thing, because my change in x is between my 1 and 4 value, and between my 4 and 7 value, and between my 7 and 10 value, and between my 10 and 13 value, all right? And then we'll have a change in y table, just to kind of make this nice and smooth. That's between my negative 6 and negative 8, between my negative 8 and negative 10, between my negative 10 to negative 12, between my negative 12 to negative 14. I find this kind of helpful over just the arrows. It sort of breaks everything down into little boxes and spaces for me. So just for this lesson, I want you to go ahead and do the boxes, and then later, if you rather just do the arrows, you can, okay? And then for each of those changes in x's and changes in y's, I want a rate of change, which is my delta y. So let's remember this is the y over delta x, okay? So I'm going to have one here, and here, and here, and here for each of those. So we're just going to kind of set that up. And remember, I'm going to subtract bottom minus top. And if I subtract bottom minus top, 4 minus 1 to get 3, if I subtract bottom minus top with the x, I have to also subtract bottom minus top with the y. It's ultimately not important whether you do bottom minus top or top minus bottom. What's important is you do the same direction on both sides for x and y. You have to pick a direction and stick to it all the time, okay? That's what's most important. I'm going to go bottom minus top just to be consistent, all right? So we're not wondering which one is it. Let's just always do bottom minus top, and we don't have to wonder. That's all, just to keep it simple. So I'm going to do negative 8 minus negative 6. Grab your calculators. Negative 8 minus negative 6 is going to be negative 2. So then delta y, that's my negative 2, over divided by delta x, 3, is negative 2/3. That is my rate of change between x equals 1 and x equals 4. That's my first rate of change. So that was doing just one of these problems will help us practice finding rate of change 4 different times. That's why I wasn't worried if you were still struggling. So we're going to do these a little more quickly now, because we have a lot of them to do. Okay? So then I have 7. Again, I'm going to do bottom minus top. 7 minus 4, which is 3. And negative 10 minus negative 8, which is negative 2. and then delta y, my delta y is my negative 2, over delta x, which is 3, equals negative 2/3. Oh, my rate of changes were the same. Am I done? No, I have to check them all, because if any one of them is different, it's not linear. So I'm going to keep going. Let's grab another color of pen. Go yellow. So bottom minus top, 10 minus 7. 10 minus 7 is 3. Negative 12 bottom minus top minus negative 10. I have to watch all those signs. Is negative 2, so delta y, negative 2, divided by delta x, 3, negative 2 over 3. It's looking good, but I still have to check the last one. Bottom minus top, 13 minus 10 is 3. Bottom minus top, negative 14 minus negative 12 is negative 2. You have to do this on paper with your pencil. Have your IXL notebooks out. 3, so, I got careless. Okay, delta y, that's my negative 2, divided by delta x, that's my 3, negative 2 divided by 3. Are all of my rates of change the same? Do I have a constant rate of change? Yes, they are all the same, so this function is linear. Function is linear. Why? Because my rate of change is constant. That's my justification. My rate of change is constant. Okay, so we're going to work 3 more of these together, and then we should be just about done. So look at A, and let's go ahead and set up our table real quick. Remember, we're looking at negative 1 to 3, so we want a box for negative 1 to 3. We want a box for 1 to negative 1. We want a box for 3 to 1, and a box for 5 to 3. These are where our boxes go. Okay? Alright, and we've got delta x, delta y, and our rate of change, which is delta y over delta x. Go ahead and find your delta x's. Just go straight down, find your delta x's real quick, and check them. Okay, so we should get negative 1 minus negative 3, which is going to be positive 2. And then here, 1 minus negative 1 is also positive 2. 3 minus 1 is also positive 2. And 5 minus 3 is also positive 2. Okay? Now, go ahead and find your delta y's. So remember, we're subtracting bottom minus top. Bottom minus top. Find your delta y's. I'm going to do this in a different color. I think that'll maybe help me out in keeping them straight. Okay, so 12 minus 10 is 2. 16 minus 12 is 4. 18 minus 16 is 2. 22 minus 18 is 4, right? Did I get that right? 2, 4, 16, 18 is 2. 18 to 22 is 4. Okay? Then my rate of change is delta y, 2, 4, 2, 4, over delta x, 2, 2, 2, 2, which simplifies to 1, 2, 1, and 2. So is this linear or nonlinear? Well, I do not have all the same rate of change, so this is nonlinear, because, and simple, the rate of change is not constant. I feel like 12 to 16, 16 to 8, 16, 17, seems like I did all my subtraction correctly, okay? So, there we go. If our rate of change is off even once, it is non-linear because our rate of change is not constant. It is not always the same, all right? So, let's move on to the back, and let's try C real quick. Okay, we'll set up our table. For time, I'm going to move on. I want to do one of these horizontal ones so you can see how the horizontal looks. So this is a little bit strange because it's horizontal, but it's the same basic idea. We'll just set up our delta x up here. Delta x, and we're going now, so left, right, up. We're just going from x to x, so I'm just going to go like this. Oops, wow, can't even do an arrow now. Okay, so here's my boxes. Okay, and my boxes. And then here's my delta y. And we'll continue these down to find our rate of change. Okay, so -7 minus -4. In this case, because let's see here. Yeah, because I'm going from the lower values to the higher values. I am, what is that, negative? That's fine, -3. Yeah, that's fine. -4 to -1, -3, -1. Or wait, am I subtracting? Nope, I wasn't subtracting. That's my, I was like, see here, subtract. -7 minus -4. Yeah, it's -3. -4 minus -1, -3. -1 minus 2 is -3. 2 minus 9 is -3. Cool, that looks good. 5 minus 4 is 1. Oh, let's get a different color here. Blue. Now remember, if I did left minus right, I have to do left minus right. 5 minus 4 is 1. 4 minus 3 is 1. 3 minus 2 is 1. 2 minus 1 is 1. Okay? Then my rate of change is change in y over change in x. So let's put our change in y's first. Change in y over change in x. Oops. Wrote the wrong thing there. Change in y over change in x. -3, -3, -3. So is this linear or nonlinear? Well, all of my rate of changes are -1/3. So this is linear because my rate of change is constant. I always had the same rate of change, or always have the same rate of change. Okay, so that is how you'll work your IXL skill. And then we have, real quick, defining slope as a rate of change. So this is just a concept. You're going to have some practice questions on it on quizzes or formative, and it's just on some key concepts here. Okay, so we have the slope of a non-vertical line is the ratio of the change in the y coordinates to the change in the x rise, to the change in the x coordinates run as you move from one point to another. That's a lot of words, so let's break it down. The slope of a non-vertical line. So Remember, I mentioned we'd see this non-vertical again. We cannot use slope with x equals a number. Okay, so for instance, I can't use slope with x equals 7, for instance, because that would be a vertical line, and I cannot use slope with vertical lines. Vertical lines have an undefined slope, all right?